Today I'm going to spend the class just working on problems, and I hope you have some questions of your own so that we can discuss them, because you know your first quiz is next class period, which is Tuesday. So let me just start doing the first one. Says something like this. An intersatellite relay allows messages from one satellite to another without passing through an Earth station. So this is a lot of systems that we have today actually send data to satellites, and then you have a network in the sky that relays the data. It says here, calculate the path length and the minimum distance between the radio path on the surface of the Earth for a link between two geostationary satellites that are 110 degrees apart. So here's the situation we have. This is our geostationary orbit. This is the Earth seen from above, which is looking at the North Pole, right? And then you have two satellites that are 110 degrees apart. So this is satellite S1 and S2. This is the problem number 1 in your textbook, so that's why I'm not writing the text. You have just taken from the textbook. And it says calculate two things. First, calculate this distance here, d, and then calculate this hp, the height of the path above the surface of the Earth. Obviously, d is important because of the link budget consideration. You want to be able to estimate the path loss between the two. But hp is important also to understand how much of a clearance you have above the atmosphere. Because if you're propagating through the atmosphere at some frequencies, atmosphere introduces significant losses, and you have to take them into account. So how do we calculate d? Just a little bit of geometry. This is our GS. It's essentially the radius of the geostationary orbit. And we say our GS, we calculated it in an example last time, is 42,134 kilometers. If you look at the example that we did towards the end of the last class, then we calculated this number from the requirement that your orbit period is exactly the one of the Earth rotation. Now, if I look at this triangle here, this is RGS, and this is D. So using the cosine theorem, I can write that D squared is equal to RGS squared plus another RGS squared, this one minus 2 times the product of the 2 times the cosine of the angle, RGS squared times the cosine of the angle theta, where this represents the angle theta, the angle between these two satellites. If from here, D squared is equal to RGS squared, 1 minus cosine of theta, and in our particular, so therefore D is equal to, I guess, RGS here, square root of 2 times 1 minus cosine of theta. And when you substitute the numbers, this becomes 42,134 kilometers times the square root of 2 times 1 minus cosine 100 and let's say 110 divided by 180 times 5. And I deliberately write this to remind you that our calculators are in radians. So there's one another.
Sir, how did you get theta?
How did I get theta?
Yeah.
It's given in the problem. It says calculate the distance and the height for the two satellites at 110 degrees apart. So theta is given. Theta is 110 degrees. When you calculate this, this is 69,028 kilometers between these two satellites. Now, how do we calculate this HP here? If you look at now this triangle here, between this point, and this point, you notice that this is a right angle triangle with this being d over 2, this being RGS, and this being radius of the Earth plus the height of the elevation of the spot.
So it was problem one, which chapter?
We're in chapter 2.
But this is not the first probable method, I guess, right?
Yes, that's not the
Yeah.
first problem.
No?
It's
Which
not the
one?
first one, maybe the fifth or
Okay, it's one of them.
one of them, yeah.
Sorry, one of them. Chapters. Textbook, so let me just put here chapter 2. But it's not the first problem, it's one of the problems. So how do I calculate the HP? I can say HP here is going to be equal to square root of RGS squared, this side, minus D over 2 quantity squared. And then this minus the radius of the Earth. Right, this taken as square root minus the radius of the Earth. So when you substitute the numbers, you get, I guess, square root of 42, 134 squared minus 69,028 divided by 2, quantity squared, minus 6,317, and everything given in kilometers. And then calculating HP, or when I did the calculation, this is 17,789 kilometers. As, I don't know if you remember, but the atmosphere, we say it's, let's say 300 kilometers above the surface of the Earth, or maybe 400 if we're generous. Therefore, this is far above the atmosphere, and then for the entire length of this path, it's safe to assume that you have free space, provided that your antenna beamwidth is narrow enough so that it doesn't radiate outside of this narrow cone. So you do truly have a free space between these two. Now that's the part A. Part B says what the.
Sir, one question. Is HP divides data into 55, 55 degree?
HP is this height here.
Yeah.
So what is
Well, if we assume that it's two triangles with 90 degrees, that way this data is divided into two angles with 55, 55.
Here?
Yeah.
Yes.
So we can easily find it using RGS equals to HP times cosine theta.
HP, no, this is HP plus RE, right? You can say, yeah, this is what he's saying. You can do it that way, right? You can say alternative.
It's shorter.
So method 2. I mean, he's saying cosine of theta over 2 is going to be equal to HP plus RE divided by RGS, right? And then from here, you can say that HP is equal to RGS cosine of theta over 2 minus RE. And then if everything is right, you can substitute the values and get the same result. It's a simple triangle. I didn't think of it, just the first way it came to mind. The second thing is, what is the maximum separation between these two satellites so that they have the line of sight, right? So maximum separation, maximum angular separation. When are they separated? If you start separating them more and more, you see that this height becomes smaller and smaller, and then the question is, how low do you want to go? And I guess the lowest you can have is HP equals 0. So the largest separation,
it's It's going to be 2RS. RGS.
Is for HB equals 0. And if you have HB equal to 0, then you have RGS squared minus D over 2 squared is equal to RE squared, because you still have to have the radius of the Earth. And then from here, it is easy to calculate that D is going to be the square root of, or 2 times the square root of RGS squared minus RE squared. And when you substitute the values, you end up with 2 times square root of 42, 134, 150 squared minus 6378, 150 squared, take the square root. This gives you 83, 296 kilometers. And the angular separation, in that case theta, becomes 2 times, I now calculated as arc time or arc sine or sine inverse of D over 2 RGS. If you look at when this is over here, then the sine of this is going to be this over this distance. And when you substitute the values, you end up that this is 2.83 radians or 162.27 degrees. So that's how maximum you can have them, and you can see easily that with 3 satellites you can get the full connectivity, right? You cannot do it with 2 because 2 would give you just 320 degrees, right? So you have to have 3 satellites, but with 3 you can placing 3 satellites around the globe will give you visibility everywhere where you see geostationary satellites. Later on today, I'll look at the problem differently, and I say, well, you cannot see the geostationary arc from everywhere in the world. You'll see that if you go far up north, then you will not be able to see geostationary arc.
I have a comment question. Now, by increasing the separation, are you basically shooting through the atmosphere then at one point?
In this case, you are, right? This is the maximum, right? But you would not do this, right?
It's not.
You would set this, let's say, to 300 kilometers at least to be clear, and this will kind of even reduce this somewhat, right? But theoretically, you can be talking at frequencies through which the atmosphere is kind of transparent. Because I didn't say anything about frequencies, and we'll see later in the course there are some frequencies for which atmosphere is significantly impacting the path loss, and there are some for which it's not.
It'd be the higher frequencies, right? The atmosphere.
Yeah, the higher frequencies you are generally being impacted by all the hydrometeors and all the stuff like that in the atmosphere. Now, interesting comment I have here is further reading. Google TRDS. So it says here Google TRDS. Those are the NASA relay satellites that are doing exactly this thing that we described here. Because if you place three satellites strategically, then if you have a low orbiting vehicle, for example, International Space Station or shuttle, then you can actually be in a constant connectivity with the ground, right? Because these will be connected to the appropriate hubs. And as you fly, you just hand over between these different satellites and maintain the connectivity. This is very important for NASA when, as I mentioned last time, if you want to start putting humans, people in space, then you don't want to lose connectivity to them. You want to be connected all the time. Now, what makes this really kind of cool is this morning driving to FIT on WFIT, there was a news tonight, 9:05, on Atlas V rocket, there will be one of these TRDS satellites is going to be launched. Right? So they're actually now, I think it's a 3rd generation of these satellites, so they are replacing them and bringing new ones into service. So it's going to be broadcast, so if you go to the NASA website, just look at it. I mean, it's a cool thing to look.
We have J and K. Which one is it?
I don't know, I didn't have a chance to look at it, but it's one of those. All right, so let me work another problem here. It says, so I should really write at least a little bit of text so that you can recognize which problem it is. It says a satellite is in a 322 kilometer circular orbit. And it says determine a orbital angular velocity, orbital in radians per second. Part B says orbital period in minutes. And part C, orbital linear velocity. In meters or in kilometers per second. So in meters per second. Meters per second. These are just basic calculations that test your understanding of Kepler's laws and kind of give you some intuitive feel about how these things are flying around the globe. So how do you determine angular velocity? Well, angular velocity we usually use this eta symbol is 2 pi over the period, right? Over duration in one period, you're going to traverse the angle of 2 pi. So what's the angular displacement? I guess per unit time, it's 2 pi divided by t. Now t is not given, but what's given is a. And since it's a circular orbit, the semi-major axis is the same as the radius. And we know that t squared is equal to 4 pi squared over mu, where mu is the Kepler's constant, times a to the power of 3. So in this case, this becomes, you can actually, I guess, I just substituted this into this, so you end up mu equal 2 pi over square root of this quantity here. So square root of 4 pi squared over mu times a cubed, right? When you just substitute t is the square root of this. And when you substitute the numbers, well, first, let's do a.
Yeah.
When I tell here, this is elevation, right? So this is how far above the surface of the Earth. In these equations, a is measured from the center of the Earth. So you have to add the radius of the Earth. So this becomes radius of the Earth plus the height of the orbit. And in this case, it's 6,378 plus the height of the orbit, which is 322, everything in kilometers, which gives me the semi-major axis or radius of 6,700 kilometers. So now when you substitute everything here, you get that eta is equal to, and this here, I worked a little bit more. So pi and pi cancels, 2 and 2 cancels. So this ends up being the square root of mu over mu cubed. So this is 3.986 times 10 to the 5 kilometers cubed over second squared, divided by a, which we calculated as 7 kilometers, but the whole thing to the power of 3, and then I need to take the square root of this. So when you calculate this, this is about 1 milli, okay, it's 0.00151 radian per second, or roughly 0.065 degrees per second. So that's how fast the International Space Station moves across the sky. The orbital period in minutes, well, we have the period here calculated, so let's just calculate expression for the period given
Or
here.
we can use the above.
Huh?
Or we can use the above equation. It's gonna
Yeah,
be-
this one.
Uh,
This one, right?
The first one.
Yeah, if you have,
Yeah.
okay. True, but I can use this one too. Right? So that's what I did here, right? So T is equal to, I guess, 4 pi squared times a cubed over u, taken square root. So this gives us 4 pi squared times 6,700 quantity cubed divided by mu, which is 3.986 times 10 to the 5. Let me just write this out. Kilometers cubed over second squared, and then take the root here. And this gives you the 57 seconds, which is roughly 91 minutes. Hour and a half, right? And that's the order of magnitude, plus minus few minutes for the LEO satellites, the ones that are flying around close to the ground. And then the last one, what is the linear velocity? There. Linear velocity, so that's our c, is going to be equal to the length of the path, which is going to be 2 pi times
A.
the a, and then divided by the period of the orbit. So in our case, this becomes 2 pi times 6,700 kilometers divided by 50 or 57 seconds, which is 7.71 kilometer per second, or 7.714 meters per second. So there, that's a respectable speed, right? If you're moving very fast. Okay, let me go to another problem. This is problem number 3. It says orbital measurements of Italian satellite 0. So this is satellite at 0, 0, 0, 0, 0, 0 universal time on March 26, 1979. Right, so that's kind of reveals when the first edition of this book was written. Are these? You have a semi-major axis. A is 42, 167, 4911 kilometers. E is equal to 0.00033. And then mean anomaly is equal to 28.8866. So this is mean anomaly. Oh, anomaly. All right, so the question is determine part A, the period in hours, minutes, seconds. B, determine orbital angular velocity. Determine maximum and minimum distances, so R perigee and R apogee. And D, the time of the next perigee. So let's time of the next edge. Okay. Similar problem to the previous one, just kind of exercise these things. So, how do we determine period? We're going to determine that from second Kepler's law. So this is 4 pi squared over mu times AQ. Everything is given in this equation, so you can say that period is equal to 4 pi squared over 3.986 times 10 to the 5 kilometers cubed over second squared, and times 42,167 167, so that had 911 kilometers, everything cubed, and then take the square root of it. And when you calculate this, this ends up being 86,175 seconds, which is 23 hours, 56 minutes, and 15.6 seconds. So that's a geostationary satellite orbiting the Earth in a day. These things should be 1 day, so we're a few seconds off, I guess, we'll be around. Now the part B is what is the angular velocity. Angular velocity is 2 pi over p, which in this case I have 2 pi over 86,175 seconds, and this gives me 0.073 milliradians per second. So times 10 to the minus 3 radians per second. So that's the kind of the rotation of the Earth. This is how fast the Earth is rotating, 0.073 milliradians per second. Now, the interesting thing is how we determine our perigee and our apogee. If you remember our equation for R, it was P1 plus E cosine of phi 0. That's the, or R0, right? That's the equation that we have that describes the path of the satellite in its elliptical orbit. R0 is the radius taken from the center of the Earth towards the position of the satellite on the elliptical orbit, and phi 0 is the angle in that plane. It's sometimes referred to as true anomaly or the true angle in that plane. Now, E is the eccentricity. Now, this phi 0 can go from 0 to 360 degrees, and the radius is the smallest when what I have downstairs is the largest. When is what I have downstairs is the largest? When the phi is equal to 0, therefore cosine is 1. So I have that my R perigee, the location of the closest point to of the satellite to the Earth, is equal to P over 1 plus eccentricity. By the same token, the downstairs is the smallest when the phi 0 is equal to pi, which means you're in an apogee point. This is 1 minus E, so this is the distance to the apogee, 1 minus E. Now, so that's where we start. In one of the slides, we went through the following derivation that related semi-major axis, derived this expression for semi-major axis, so this is P1 minus E squared. So from here, we can express P as 1 minus E squared times A. Therefore, you can calculate that Rp is equal to A 1 minus E squared, that stands for this P, divided by 1 plus E. And this gives you essentially A 1 minus E, that's the distance to the perigee, and then our apogee was A 1 minus E squared divided by 1 minus E, which is equal to A 1 plus E. see that. Another interpretation of eccentricity tells you how much is pushed in the perigee point and how much you are expanded in the apogee point. Now, using the actual data here, you see that RP would be 42, 167, 911, 1 minus 0.00023 is equal to 42, 153.99. It's in kilometers, and then our apogee is 42, 167.911, 1 plus 0.00033, and this is 42, 181.82 kilometers. These, this tells us what we already know, that satellites that are flying in a geostationary orbits are on the orbits that are very close to being circular, right? So there's very small difference in the distance between perigee and the apogee. So where am I? C. Then D, the time. Oh, okay, so that this one is important, and I wanted to point out something in this. Part D says determine when is the satellite going to go through the next perigee, right? After this time period. Here's the equation that we need to remember. Mu, which is the mean anomaly. Let me just write it. Mean anomaly. M is equal to average velocity t minus t perigee. One thing that you should remember, and I should have stressed that when we talked about two-line element data, but I'll stress it now. Mean anomaly is not an angle, right? If you look at the orbit of the satellite and somebody says point mean anomaly, there's nothing to point. Really, if you think about what is happening is this. Let me just draw ellipse. This is the location of the Earth. This was our coordinate system. Remember, we had this circle around that encompasses Earth. The satellite moves on the ellipse. This angle here is phi 0. This is our true anomaly, right? The projection of this point on this big circle is our tells us the angle of eccentric anomaly, this angle, right? Nowhere here you're going to find the mean anomaly, right? Mean anomaly is an average angle, right? You see, it is this nu here is an average angular velocity. For circular orbits, right? If the orbit is perfectly circular, then nu is constant, and therefore m becomes the same as phi 0. But for any non-circular orbit, m is just an average angle angle traveled around the circle. It's not the actual one. So sometimes in this area here you're going to be ahead. In this area here you're going to be behind, right? Because here the satellite moves faster than m, and here it moves slower than m. So it is not a real angle. It just helps us do the calculations. Because you remember, it is very easy to calculate nu because we know the orbital element, so we can calculate the period. 2 pi over period is nu, so we can easily calculate m. And then through that transcendental equation, m equal e minus e sine of e, we can calculate eccentricity, and then we calculate r0 and phi from eccentricity. So just keep that in mind. There is nowhere in this graph where you can actually draw mu. But let's look at our problem here. So what we need to, so here's the satellite going through Perigee, right? So this is satellite, this distance here is RT. And it says here, when this data were taken, it was at midnight on March 26, your mean anomaly was 28 degrees. So you were, on average, 28 degrees away from this point. What you can do is you can calculate first nu. And nu is equal to 2 pi over t. And in our case, or I have it here, because I don't have t, I have, or I do have t, or I even have nu.
We did in part B.
We have nu, right? So here it is, right? So I don't have to count. Just say, I know nu, it's 0.073 milliradians per second. Now, since I know nu, I can, and I know m, and I know the current time, which is the time at which I'm taking a measurement, then I can calculate what was the time when I went to Perigee. It's going to be negative, right? Because I went to Perigee before this point, right? I'm already 28 degrees on average away from Perigee. So I went to Perigee some time ago, right? So by calculating what the TP is from here, TP is going to be equal to T minus m over nu. And in our case, if I fix our current time to be 0, this becomes 28.866 degrees over 180 degrees times pi, divided by 0.073 times 10 to the minus 3 radians per second. So this gives me minus 6.881 seconds. So again, how can the time be negative? Well, relative to the time where I'm taking the measurements, this is where I went to Perigee. So it was 6,800 seconds ago, right? And when you calculate this, this is, turn this into hours, so this is minus 1 hour, 54 minutes, and 41 seconds ago is when I went to Perigee. Now, when is the next time I'm going to go? I have to add my period, right?
Yeah.
To this value. So this is when I went to Perigee, and then again, 24 hours after that, I'm going to go to the Perigee again. So I call this T Perigee nu is going to be minus, and I write this in this notation, 0.1, 54, 41, 41, plus 23, 56, 15.6. And these are time, obviously, 1 hour, 54 seconds, 54 minutes, 41 seconds, plus 23 hours, 56 minutes, and so on. This gives you 22 hours, 1 minute, and 33.9 seconds. So that's the next time you're going to loop around and go to the position where you're closest to the Earth. Okay? Any questions here? Okay.
Excuse me. So the TP mu is different every night?
Which one?
TP mu.
No, this is okay. This is when from if I'm calling, I just erased it, this time 0, right? How, if I set my stopwatch, what is going to be the time when I go to Perigee again? So if I start counting the time from now, I'm going to count 22 hours, 1 minute, and so many seconds, and I'm going to be in Perigee. When is the next time that you're going to be in Perigee? Well, add this to the new period, right? So in 55 hours and a change, you're going to be again to the new Perigee. And every 24 hours roughly, you're going to go to another Perigee, right? See, the time is always relative, right? Because we call 1.0, right? Unless you talk about universe and then you start from the Big Bang. But what we do here, we say, this is when I took the measurement. I'm going to call this time 0, and then I calculate relative to this. That's what we did here. We called this time 0, and we said we went to Perigee an hour ago because we are now at the mean anomaly of 28 degrees. Right? And then when is the next time I'm going to be closest to the Earth? And this is how long it will pass. And then next time is in another 24 hours. So this is problem number 4. The authors of the book are from Virginia Tech. So it says Virginia Tech Earth Station is located at L Earth. I think we use these small ones. So L Earth is 80.438 degrees west, and latitude of the Earth station is 37.229 degrees north. So that's the location. The small lowercase l is for longitude, and the uppercase L is used for latitude. So this is where the Earth station is going to be. It says calculate the look angle to geostationary satellite whose sub-satellite point LS is equal to 121 degrees west. What is LS? What is LS? What is the latitude of this sub-satellite point?
0.
If this is a geostationary satellite, its latitude is on the equator, so it's equal to 0. It's not mentioned in the problem, but I just have to I just asked you. So now, when you look at this longitude here, we said that everything that is west is taken with a negative sign. So you would convert this into minus 1.4038 radians. Right? That's the latitude. Now, whatever is in longitude. In latitude, whatever is north is taken with a positive sign. So let me kind of draw this again, because you guys need to know this to use that spreadsheet that we have properly. So this is 0, 0 point. This is plus latitude, and this here is plus longitude, right? So this is also north. This is here east, west, and then here it's south. So when I say, let's say Florida Tech is at 28 degrees north and 80 degrees west, so that means its latitude is positive and its longitude is negative, right? Because we are west of the Greenwich. So in this case, you have Virginia Tech, that's 80 degrees west, so it's somewhere here, and 37 degrees north, so it's somewhere here. So this is Earth station, and then the sub-satellite point is 128 degrees, so it's here. Right? So you kind of, it's good to draw this because it tells you a little bit, you know, at least where your remember, there are two angles that we need to calculate. One is elevation, and the other one is the azimuth. Elevation is straightforward. It's not complicated. Azimuth has all of these cases. So always catch this, because it's very easy to pick the wrong case, right? And in this case, you can see, okay, it's not 270, it's not 180, but it's in between those two, right? If you're standing at Virginia Tech, you're not looking due south, which would be 180. You're not looking due west, which would be 270, but somewhere in between, right? So when you calculate, the end result needs to be somewhere in between, right? That's how you build the check of make sure that you don't make mistakes. And then the radius of the satellite, RS. So this is, what did I calculate? Did I calculate this? No, I didn't. So 0.6496 radian. And this guy here is minus 2.1118. This is 0. RS is the equal, satellite is 42.34 kilometers. Because the satellite is in a geostationary orbit. All right, so let's do calculations. There are two angles that we need to calculate. We need to calculate elevation, and we need to calculate azimuth. And out of the two, elevation is the easy one, so let's calculate elevation. Calculation of elevation. Elevation is calculated in two steps. In first steps, you calculate that intermediary angle gamma, and then in the second step, you calculate elevation. So step 1, you say cosine of gamma is going to be equal cosine of the latitude of the Earth station, cosine of the sub-satellite point, cosine of LS minus LE, plus sine of the LE sine LS. You know, this is a general case. In a lot of times when you have satellites that are on an equatorial plane, this calculation simplifies. You can see right away because your LS is 0, this becomes 1, this becomes 0, so the second term goes away and it kind of simplifies quite a bit. But let me do the justice to this equation here. So I'm going to write cosine 0.64976 times cosine of 0 times cosine of minus 2.111848 minus 1.4038, and then plus sine of 0.64976 times sine of 0. I wrote everything out so that you can kind of map this substitution to this, see what's going where. And these signs, make sure that you pay attention to that. But this ends up being relatively easy to calculate, so this is 604861. So that's the cosine of the gamma. Therefore, gamma is cosine inverse of 0.60486, and this gives me angle of 0.921205 radian. So that's the step 1. You calculate this angle gamma. Step 2, you actually calculate the cosine of the elevation. So the cosine of the elevation is going to be equal to sine of gamma divided by square root of 1 plus radius of the Earth divided by the radius of the satellite squared minus 2 times radius of the Earth, radius of the satellite, times cosine of gamma. And then taking square root here. And when you substitute the values and you do the calculations, this ends up being 0.868975 radian. So now, since you know that, not radian, just the number. So now that you know how large is the cosine, you can calculate elevation as cosine inverse of 0.868975, and this gives you a value of 0.5176 7 radian, which is 29.7 degrees. So that's the elevation, right? That one is relatively easy. There's nothing to think here much. I mean, you will see, even when you look at our spreadsheet, this is just one tiny section of the spreadsheet. You punch in these numbers. As a matter of fact, you punch them in degrees, if you convert them in radians, do all the calculations, you come up with a single field that tells the elevation. Now, calculation of the azimuth is azimuth is somewhat more elaborate. I'm going to actually do it. It's done in the spreadsheet, but I doubt that you went through the fields in the spreadsheet. So let me at least go through the calculations once, and kind of go it. And then this is also coded in the spreadsheet, so it's important that you go at least once through the calculations that need to be done. So first, what I do here, I identify group and case. Group is, you remember there are 8 possibilities, and we divide them into 2 groups depending on where the Earth station and sub-satellite points are. Now, sub-satellite point is on the equator, so it can go either way, right? But the Earth station is in the north hemisphere, so it's a group 1. Group 1 is the group for which at least one of these points is in north hemisphere. Right? Here we have Earth station that is Earth hemisphere. Now, out of these 2 points, when you look at the cases, point B is the one that is located further north. Right? We have point A, point B. So you would place point A here, and this is point B. And then you have a case where sub-satellite point is in point A, and it's west of the Earth station. And if you look at those cases, this ends up being, I always have to look at it myself. So this is group 1, case 1, right? So this is case 1, right? So that's what you do first. You identify the case. And then there are some calculations that you just execute. First, you calculate C, which is the LB minus LA, just the absolute difference between the two longitudes. So in this case, this is minus 2.114848 minus 1.403. And this gives you 0.708 radian. And then we set LB equal to 0.64976 radian, and LA, latitude of the L point, is 0, because your sub-satellite point is on the equator. Now, in the equations, we have those 2 angles with respect to x and y. So we have the tangent of 1/2 x plus y, oh sorry, 1 minus x first. Y minus x is equal, and now I don't remember what stands on the right hand side, so I have it already calculated here. Just get a. So that was that expression, which is sine of 1/2 LB minus LA divided by tangent of C over 2 times cosine of 1/2 LB plus LA. Right? Everything is known in this expression. You have B and LA and C, so it can be easily evaluated. And when I did that, this resulted in 0.911469. So that's this tangent of these 2 angles. And then the next equation gives you tangent of their sum. So tangent of 1/2 y plus x is essentially something similar here, but instead of the sine, you get cosine. Cosine 1/2 LB minus LA divided by the same thing downstairs, tangent of C over 2 times, sine of 1/2 LB plus. And when I calculated this one, this ended up being 8.034313. Right? So you have tangent of this, tangent of the other one. You take the inverse tangent and you get 1/2 of y minus x. So taking tangent inverse on both sides, you end up at 1 plus 1/2 y minus x is equal to 0.7391, and 1/2 of y plus x is equal to 1.447. So now, if you calculate your x and y, you end up x being 0.708, and then you end up with y being 2.186. How do you get x and y from this equation? If you sum these two, you get y. If you take the difference, this minus this one, you get x. You see that, right? You sum, you get 1/2 y, 1/2 y, and x is cancelled, right? If you take this minus this, you get y's to cancel and x to n, right? You get y's.
Question, how do you get A and B? How do you, what do you take A and B?
How do I get A and B here, right? You look at, you end up with 2 points on the globe, right?
Yeah.
Point B is the north one, right? So out of these, you have to call one A, call the other one B. The north one is B, and the south one is A, right? So once you decide it, then you have you take the 4 cases, right? And you can have the cases where 4 possibilities, right? You can have Earth station is in A, or Earth station is in B. Earth station is west, or Earth station is east, right? So 4 possibilities. Now you have 2 possibilities. You have assigned your subsatellite to A, so Earth station is in B, and then there are 2 possibilities. The subsatellite point can be east, west, or east. And then in this case, Earth station is in B, and subsatellite point is west of B. And then that points to the case that you're considering, right? And then,
So in the southern hemisphere, is B below A?
Is it opposite?
It depends on the.
yes.
Okay.
It's B is always further away from the equator. But double check. I remember quoting it, but I don't remember.
So this part of this is kind of confusing. A and B.
It is. That's why you need to practice. Right? I gave you an example there where it's just calculating different cases. Right? And what you need to do is you need to go calculate and then test the spreadsheet. And tell me if it's wrong. Because I just coded it quickly, right? So, but it is confusing. But it's just it's not that confusing. I mean, you dealt with the more complicated things in your life. It's just that it's easy to make mistakes. Let's make it that way. You just have to be patient and kind of make sure you double check. But once you get to this point, the solving of this is trivial, and now you get these 2 angles, right? And the question is, which from these 2 angles, how do you calculate the actual azimuth? And then you go to the appropriate case, and the case gives you recipe. So for case group equal 1, and then what color called the case equal 1 in the first group, then your azimuth is going to equal 360 minus 1 in degrees, right? So you calculate x and y, but you're always going to toss one of them away, and then use the other one either as as it is given, or 360 or 180, whatever the recipe tells you. So in this case, azimuth is going to be 360 minus 2.186 times 180 divided by pi. And this gives me 234.75 degrees. Now, when I get this, you know, I have to go back and I say, well, was my guess right? And what did I guess at the very beginning, right? I said, well, it's not 180 because I'll be looking straight south. It's not 270 because I'll be looking straight east. So it needs to be between 180 and 270, right? And I look at the number I get, and it's in that range, right? It's very unlikely that that you're gonna get all of these calculations, make mistake, and still fall within proper quadrants, right? So it's very important to do this initial step, kind of ballpark it, and then do calculations, right? Because it's easy from here to kind of ballpark it, right? You can intuitively see where it needs to be, and then you do calculations, and this angle here better fall into your range. And then as a final check, you punch in the numbers in a spreadsheet and you get the result. And then if that agrees, then you are worry-free. Let me see. This one is kind of similar.
Sir, do you have any problems regarding Doppler?
Doppler?
Yeah.
Let's see. No. I didn't prepare anything. There's, I wanna, okay, let me do this one. I don't have any problem, because most of these problems that you find at the end of the book deal with geostationary stuff. So let me do this problem. In the notes, it's problem number 8. This goes, I mentioned this earlier, so let me discuss it in more detail. Determine maximum and minimum range from an Earth station to the geostationary orbit and calculate corresponding trip delay. So maximum and minimum range from an Earth station to geostationary orbit. And calculate round trip time, right? How long does it take for the signal to go to the geostationary orbit and come back? Okay, so let's take a look at here. This is first. Let me calculate the minimum. This is globe. I view it from North Pole. Standing above here. This is the geostationary orbit. When are you closest? When your Earth station is here, and you're right on the equator, and you're looking at a satellite that is right above, right? So in this case, you can see that this is what Earth, and this is I guess here is RS, or I call this the same as RGS. We'll calculate RGS to be 42,134 kilometers in one of the previous examples. We know that the radius of the Earth is 6,378 kilometers. So your distance, which is this minimum, is going to be RGS minus RE, which is 42,134 kilometers minus 6,378 kilometers. It gives you 35,756 kilometers. So that's the minimum distance. And then round trip time here becomes 2 times the minimum divided by the speed of light, right? Because you need to go to the satellite and come back, and the radio waves travel at the speed of light. So this gives us the minimum round trip time that we can experience in satellite communication when you're talking to a geostationary satellite. When you substitute the values, this becomes 2 times 35,756 times 10 to the 3 meters divided by 2 times 10 to the 8 meters per second. And when you do calculations, this is 0.239 seconds, around 0.24 seconds. So 240 milliseconds is the delay that we have in talking to the satellite. Now, the next thing is, let's calculate the maximum. Now, again, the picture from the above, this is north. You are, again, here in a geostationary orbit, but you are talking to the Earth station that is somewhere here. So that's how far before you're obscured by the globe, right? Before your satellite falls below the horizon. Now, when does this happen? This angle here is what? This will be 90 degrees. This is RE. This is RGS, and this is your D max. Right? That's what happens at the maximum point. So here, I say D max is going to be square root of RGS squared minus RE squared. And when you calculate, this becomes square root of 42,134 squared minus 6,378 squared, which gives you the 41,648 kilometers. So this is how far you can be. And then round trip time max, right? This was round trip time min, would be equal 2 times D max over C, which in our case is 2 times 41648 times 10 to the 3 meters divided by 3 times 10 to the 8 meters per second. And this gives you a round trip time of 0.278 seconds. Right? It is wrong in the notes, so it says milliseconds, but it's not milliseconds, it's seconds. So, or roughly 280 milliseconds. So your round trip time is somewhere in the interval between 240 milliseconds to 280 milliseconds, just for the propagation time. This does not take into account the time required to process the signal on board of the satellite. Now, how important is this? Well, if you're talking about broadcast, television, even data services, this time is negligible, right? You don't notice that. But if you start with about quarter-second delay just for propagation, and add about, let's say, half a second, of all the processing on board the satellite, you start reaching, let's say, close to a second delay. Now, what happens is, and in older satellites it can be even more, right, depending on what the processing is. Now, we as humans, if the delay is smaller than 600 milliseconds, we don't notice that, right? That's the difference in talking to, let's say, a very young person and kind of old person, older like me, because we process slower, right? So you slow down as you age. but you don't have problems. If it's below 600 milliseconds, that's, depends on a person and so on, but that's taken as a technical number that we all use. Delays smaller than 600 milliseconds do not impact the quality of your perception of that communication service when you're on a telephone. Now, when it starts being larger than 600 milliseconds, we notice that delay. We notice as first we interpret it as a hesitation on the other side, but then we notice it's actually delay. The old satellite systems were actually much worse than that. You could have a second or even 2-second delay. And in that kind of environment, you actually have to discipline yourself. You have to say, okay, I understand that there is a delay. And then you say something, and then you wait for the response. Because initially when you start conversation, it happens that you say something, the other person doesn't respond, and you start talking, and then the other response comes back. Right? So we have to discipline ourselves. But it's good for you to remember about quarter-second delay is the round trip time to the geostationary satellite just due to the propagation. And this is half of the allowed delay, right? You can add about 300-400 milliseconds for processing and be on a safe side where you result in imperceptible degradation due to the delay. But if you start exceeding the 600 millisecond budget, then you start noticing that there is a delay on the line. Quickly, I just want to do another problem. That's problem 9. It says, it's kind of the variation of this problem. It says, determine the maximum north latitude at which you can see the geostationary arc. So this is now exactly the same problem, but now you are viewing Earth, sideways, right? And the geostationary orbit is here, and then you kind of see, well, how far up north can I be to see this satellite, right? I have this equation where this is RGS here, this is our D max, this is RE, and I'm kind of interested in what this angle is. How far can I go up north? Because this angle is actually latitude, right? It's the angular distance from the equator. How large this can be for me to see the satellite. And you can easily see, for example, cosine of the L max, right? Of L max is RE over RGS. Right? It's RE over RGS. Therefore, L max is equal to cosine inverse RE over RGS. And when you calculate that, this is 1.42 radian, roughly 81.3 degrees. So you can cover up to latitude about 80 degrees. Now, as far as United States, do you know how far we go? We go about 50-something degrees up north. So from everywhere in the continental United States, you can see geostationary arc, except where? Except in Alaska. Alaska is up north, right? So you have to, when you're dealing with far north latitudes, then you have to take this into consideration. And as I said, in the United States, we just worry about Alaska. Canadians worry for their northern territory, and Russians worry for almost their entire, northern part of the country. Covering those is relatively difficult because you cannot have geostationary satellite to see them. So you have to have satellites that kind of fly like this, right? And what they do is Russians design a specific kind of orbit. It's called Molonia. It's an inclined orbit that is it's also quite a bit eccentric. So it is kind of going around the south part of the globe relatively fast, and then it kind of wells over the northern part of the globe and goes like this. And then in the meantime, the whole Earth rotates, so you would actually have to have multiple satellites to keep a constant climb. Okay. So these are the problems. There are a few other problems that are, I just skipped because there are variations on the problems that I have already covered. Do these problems, do our examples, do the examples in the book. What you should expect 10 really short problems, each work the same point, like not too elaborate calculations, but something that requires you to kind of understand this. You cannot study on the test. And bring your calculator, bring a formula sheet, and stay away from cell phone. You have a cell phone, and other than that, that's it. You know, you can drop by my office hours for the last minute stuff next Tuesday.